Good morning, everyone. This is Mr. Bronze. Welcome back. Hope everyone had a great holiday and a happy new year as well. Here we are on Monday, January 4th, 2021. And as most of you are probably thinking, thank goodness 2020 is done. I'm still not back, obviously. Shooting for next Monday is the most probable date I will be returning to the building. Mrs. Bronze is making some good progress. It's just a little bit slower than we had anticipated. We have to make sure she's in a good place before I leave her alone for a good part of the day. So I want to say thank you to all the well-wishers out there. Got some nice emails from some students and much appreciated. All right, so with that said, you probably saw in today's stream that we had a little worksheet, and hopefully you have that pulled up now. What I kind of want to do today is just, get your brains firing on all cylinders again. It's been a week and a half. You've been out of school, and statistics is probably the last thing that was on your mind during that time. So today will just be a nice little activity. So the worksheet consists with a total of 7 questions. So this video, we're going to go through the first couple together to kind of get the juices flowing again, get you feeling good about what we talked about in Chapter 15 before the break, because tomorrow I do want to open up and begin Chapter 16. Okay, so why don't we get things rolling then? So here's question number 1. A very small amount of information given, as you can see. We have 2 events, A and B. The probability of each one of those events, probability of A, 0.48, probability of B, 0.67. And then we have the probability of the intersection of A and B at 0.22. So remember, intersection, that upside down U, also is a symbol for the word and. So the probability of A and B both occurring simultaneously. So something like this, a lot of us are visual learners, and we've talked about that a lot this year, about drawing pictures, graphs, charts, whatever is necessary to really get our heads wrapped around the question, being able to sink our teeth into it. Let's get ourselves a Venn diagram going here. So you guys probably have this open in Kami, I would hope. And you have your tools on your left toolbar there where you can create your various shapes. So why don't you go ahead and use that and make yourself a Venn diagram, as I'm doing the same here in the Smartboard software. Make sure that once you got the Venn diagram that you do label, because we have our 2 different events, A and B, so we want to label the 2 different circles that we have there so we keep track of our data values. And also, if we were to look back at this at a later date, everything is very organized and easy to interpret on our Venn diagram. Okay, and for the sub in the room, if you need to pause the video at any time for the students to catch up, if I'm moving a little too quickly, please feel free to do that. Thank you very much. All right, so when we're working with the Venn diagram, as we know, and you have plenty of experience with this, we work from the inside out. So you want to begin with this football-shaped piece here in the middle, which represents the intersection of our sets A and B. And that's where our number 0.22 fits in very nicely. So I'm going to grab a little text box. I'll make this even smaller so it fits in nicely. There we are. So we're going to put our 0.22 in there to show that is the probability of the intersection of these 2 events. Okay, so now we begin to work outward. Let's start with event A. We need to fill in these crescent moon shape here. Now we know the probability of event A, which is the entire circle, is 0.48. So if this part of the circle is 0.22, we can subtract it from the total, 0.48, to realize what our probability is for the remainder of A. And when we subtract, 0.26. So go ahead and put that label in there. Excellent. We're going to move over to the crescent shape here in B as well. Probability of event B occurring is 0.67. And remember, that's our whole circle. We're going to subtract from that the 0.22. And we wind up with 0.45. So as of right now, we have all the various pieces of both events A and B. But what we don't want to forget is this. There could be the possibility that neither event occurs. Remember, everything inside of the rectangle has to add up to 1. So if we were to take our values 0.26, 0.22, 0.45, and then add them all together, we want to make sure we've got that a total. And if it doesn't reach 1, which is 100%, whatever is missing to get us to 1, that's that our floating value out here. As a matter of fact, when we add these together, we get 0.93. So that means 93% is contained within our events A and B, and that leaves that small 7% that is in the rectangle, but not within either one of our events. We'll drop that right down there. All right, so we have our entire, let's just get rid of this. There we go. We've got our entire Venn diagram filled out. And this is going to make answering our questions a lot easier. So let's start at the beginning. So here, we're asked for the probability of A or B. A or B. So the union of sets A and B. So the union means we want to add up the probabilities contained within both sets. Now, having a visual eliminates the need for thinking about what a formula looks like and double counting and all that other nonsense, because we can see that the probabilities contained within our two events A and B would be the total of these three numbers. And that actually we just determined a few moments ago as 0.93. This is our answer for our first part. Okay, off to the second part. Now, looks a lot like A, but we got this little guy here in the superscript, the exponent position. It's a B with a little C up there. That means the complement of C. So that means everything outside of set B. So interesting. So if set B, and let's look at this diagram for a minute. Let's just focus on the complement of B. Excuse me. If this is set B in this circle, the complement of B is anything outside the circle. So that would mean the 0.07 and this 0.26. And we want to take those two values with the union of A. Now, we don't want to double count the 0.26 because we're already counting that, but we also are going to add in the 0.22. So for part B, we need to take the sum of 0.22, 0.26, and 0.27. And that leaves us with a probability of 0.55. Second part. All right. Now C changes things up a little bit. Now we're looking at the complement of A, and our operator has changed. Now we're looking at the intersection. So let's think about this. The complement of A. So these two values are within A. So the complement is anything outside of circle A. So not including these two. So the complement of A is this crescent-shaped piece here on the right, plus everything that's out here, which is the 0.07. So these two. Where does the crescent shape and everything outside intersect with B? So what does it have in common with B? And sometimes, adding to your picture and maybe doing a little shading will help. So the complement of A. So the complement of A is all of this, all the way out here, plus this little guy right there. And then now, where's B? Well, B is everything inside of this circle here. So now we've got an overlap. And that's what we look for intersection. Where do we have an overlap? What's in common? And that's just this crescent shape here. So we find that our probability is 0.45. Go back there. Okay. So now, Now we change things up even further. If you take a look here at D, we've got conditional probability. So the great thing about a Venn diagram, again, is all the numbers you need are right there in front of you. For example, what is the probability of selecting event B given we've already selected A? So this is our condition here at the end. This is what we're trying to find the probability of. This is the condition, comes after our symbol. So that means A has already happened. So let's put a little circle here, a little green circle around A. That's our condition. So that means we are only going to look at the values inside of this circle. Now, inside of this circle, if we were to throw a dart and it was going to land inside of this circle, what's the probability we land on B? There we go. 0.22 out of the whole circle, which is 0.48. And that's what we want to think of. With conditional probability, we are narrowing down the scope of what we're looking at. We are only looking at this circle. So you imagine throwing a dart, and it's a magic dart in that no matter where you throw it, it only lands in the green circle. What is the probability you land in the piece that's also in event B? 0.22 over the probability of landing in that circle. So we go ahead and divide that, and we come out with 0.4583 when we take that out to 4 decimal places. And as just a general rule, I usually go out 4 decimal places unless I'm told otherwise. Okay, so how about the complement of A? What's the probability we land in the complement of A given we're looking at the complement of B? So where is the complement of B? The complement of B is anything not inside circle B. Okay, so that means everything outside of both circles, which is 0.07, plus this crescent shape here, which is 0.33. So, question is, if we were to throw a dart, and the dart is only going to land in the outside section or in this crescent shape, what is the probability it lands in the complement of A, which is the outside section? So when we structured this probability of landing in that outside section is 0.07 divided by the sum of 0.07 and 0.26. That was a little tricky. Really got to focus on what areas you are looking at in your diagram. So we're going out 0.2121. All right, so now a little bit of terminology. Let me grab this guy here. Let me do this. Not cooperating. It's a little, all right, I guess my software is a little wonky. I don't know what's going on here. All right, that said, are A and B disjoint events? Disjoint. Disjoint means they are completely separate from one another, which would mean if they were, the Venn diagram would have 2 circles, much like this, that don't have any points of intersection. This is what disjoint looks like. This is not disjoint. They have something in common. There it is right in the middle. So we can say events A and B are not disjoint. We begin by answering the question, yes or no. Make this a little bit smaller. Might be too small. All right, we'll go with that. So events A and B are not disjoint because, and you can do 2 things here. You can give an explanation in a written word, in a sentence. What I prefer, and I think what the folks at the College Board prefer, is using a statistical interpretation of what you see. They're not disjoint because they have an overlap. And the overlap is here in the middle, right, where sets A and B intersect. So why don't we sort of put that into some nice notation here by showing that the probability that we have an intersection of A and B. Let's see, do we have symbols that we can insert here? Da-da-da. Okay, I'm not going to waste our time with that. We'll just move that over a little bit. We're going to get fancy here in 1 second. So we're going to say that the intersection of A and B, we're going to draw a little intersection symbol. Little sound effects there for you. Okay, it's about as good as it's going to get. Because the intersection of A and B is equal to 0.22, and then I would even take that maybe even a step further and then say, which is not equal to 0. Put a little slash for the equal sign. That right there, folks, that is a great answer, perfect from beginning to end. You've addressed the question, you've given the evidence, and you've even shown that you know the true definition of disjoint in terms of what the probability would be equal to. So that's a really, really good idea there. Okay, independent. Are events independent? So let's take a look. Now, we don't have, if we go back, and this is the thing, I'm just kind of thinking back how I want to say this. On past AP statistics exams, what you often see in a question like this is all your information is laid out. Actually, you know what? I misspoke. It is all right here. Okay, it's perfect. Are A and B independent events? I think the easiest way to determine if two events are independent is to compare conditional probability to simple probability. Here's what I mean. We have one conditional probability that describes our two events A and B. And here it is. This is the probability of B occurring given that A has already happened. Conditional probability of B. Here's the simple probability of B. Simple meaning just what is the probability of B? Done. No conditions. If they were independent events, these two probabilities would be equal. Since they're not equal, therefore, they're not independent. So we're going to say events A and B are not independent. Comma, because probability of B equals 0.67, which is not equal to the probability of B given A, which was 0.4583. I want to run off the screen. Let's just slide that over a little bit. And I just need a little slash. Right there. There we go. So you're showing that events are not independent because the simple probability of B, which is here, is not equal to the conditional probability of B, given that A has occurred. There you are. All right, great. So let's take a look at number 2. So we're told probability of G is 0.18, probability of M is 0.24, and that G and M are independent events. Okay, so that's a very important piece of information. We've got independence. So what is the probability of G and M? Well, I would, if I were you, highlight or underline the word independent. Since they are independent, we can use the multiplication rule to find the probability of both events occurring at the same time, which is an and probability. So let's go ahead and write this out. So the probability of G, I'm going to use the word and since the smartboard software isn't real hip on symbols. G and M, due to the fact that, again, that they are independent, really this is just the probability of G times the probability of n. And when we put that together, we get 0.0432. Here we are. This might be a little bit easier to, might be a little bit easier to read. Change color. There we go. All right, so there we are. So independence really, it simplifies the algebra behind what we need to do when we solve for those types of probabilities, specifically the and probabilities. All right, let's take a look at number 3. So here we have probability of W, probability of J, and the probability of J given W. All right, and we are asked to find what is the probability of W and J, and what is the probability of W or J. All right, so let's think about how we're going to put this all together. So we have conditional probabilities, right? And we have and probabilities. We've got simple probabilities. So how can we combine this all together, right? How can we give the condition or work with the condition to do our and probability at the same time? So let's think about this completely. So when we talk about conditional probability, often what we do, and let's go ahead and rewrite that. I'm going to make it a little bit easier. So if I was talking about the probability of J given W, what we do is we could break that down. And on your formula sheet that you get for the AP exam, which I'm pretty sure I've given everyone a copy of, if not, very easy to find right on the College Board website, you will see that, and we've discussed this already, this is conditional probability, is the probability of those two events happening simultaneously, which is an and probability, divided by the probability of the condition. And remember, the condition is what comes last in the conditional probability. So we can use this little formula right here. Now, you can do one of two things. You can leave it just the way it is, work with it from there, or what you can say is, well, you know what, I'm looking for W and J, which is the same as J and W. I want everyone to understand that. An intersection is commutative property applies. So whether you do W and J or J and W, we're looking at the same thing. So if I wanted to solve, I can imagine making this into a proportion and putting it over 1 and taking cross products. So what that means is the probability of J and W, which is right here, is this conditional probability times the probability of W. So let's go ahead and put that together. So that would be 0.61 times 0.2. And let's just pump this up a little bit. A bit easier to see. There we go. And when we multiply those two probabilities together, we get 0.122. There is our solution. Okay, so how about our OR probability? Well, if you notice, what makes this question, question number 3, different from question number 2 is it doesn't state anything about independence, okay? And we can't assume independence. We could try and test for independence, but we really don't need to spend time doing that. And here's why. An OR probability, and we're going to write it out here. Let's make this 18. An OR probability is quite simple. It's the probability of the first event. So it'll be W, right? W comes first here, as we can see. And we have plus, and that's traditionally our operator for ORs, the probability of the second event. But then what we have to be careful of is then we have to subtract the probability of both events happening. So the probability of W and J. And what I love about this formula is this is an all-purpose formula that works whether events are independent or not. Because if they're not independent, which is what we see here in A, we actually know they're not independent because they can. We have a conditional probability. We can see right here, J given W, the probability of J, these two are not the same. So we knew they weren't independent from the beginning. So I should have identified that a little bit earlier. But that said, my point is, whether they're independent or not, if they were independent, this would just be 0. Probability of A and W and J. So we wouldn't have to worry about that at all. All right, anyway, that said, let's go ahead and plug in what we got. What's probability of W? 0.61. Plus probability of J, 0.45. Minus probability of W and J, which is what we just solved in part A. And use a little algebra, magic of math. We have 0.938. And there is our solution. So what I'm going to do is I'm going to leave you guys to finish the last 4 questions. There's question 5, 6, and 7. I have several parts to them. If you want to, you can certainly create Venn diagrams or any other sort of chart graph that you may find useful. You don't have to. Entirely up to you. So you can use what's left in the period to work on that, finish that up, and submit the entire assignment, all 7 questions, to me by midnight tonight. And then tomorrow we will kick off with chapter 16, and then we'll talk about where we're headed for the remaining couple weeks of this marking period and when our next assessment is coming up as well. All right, so as always, if you have any questions for me, please don't hesitate to either put them in the stream, or you can go ahead and email me and let me know if there are any issues. All right, once again, welcome back, guys. Hope you all have a great day, and I will see you tomorrow. Bye-bye.